Hey there, this is Dylan. So the molecule that we're working with is arsenic pentafluoride. First thing we want to do is we want to figure out how many electrons this has in total. So we have one arsenic times the 6 valence that it has, plus the 5 fluorines times 7 valence per each fluorine molecule. You're going to get a total of 40 electrons, which is equal to 20 pairs. So, next step, you just want to draw the basic Lewis-Dog structure for it. Doesn't really matter how you look at it, just make it look really nice in the sense that you can tell where everything is and it looks as accurate as possible. So we know that it's bonding to 5 things. You have your fluorines that you're going to go ahead and add in there. And just make sure you get those electrons, the lone pairs around the fluorines. Show that it's complete octet. Okay, and then now that we do have the Lewis-Dog structure, let's move it over just a tad. Let me go ahead and move these pictures out of the way real quick, actually. If I can... Well, this picture is going to have to stay there. So, let's actually move this up just a tad. So, first thing you need to figure out is how many electron groups it has. Then we're going to figure out how many bonding pairs it has, and then how many lone pairs that it has around the arsenic atom. So just your central arsenic. So first things first, let's find its electron groups and what its number is. So we can tell that it has no lone pairs, but it is connected to 5 different fluorines. So the group number is going to be 5. How many bonded pairs does it have? 5. And we can tell that it has no lone pairs because you don't see any electrons not bonded to any fluorines around the arsenic. By this information that we write down, let me move this up a little bit more again. So we have that. Now, with this, we can tell that the electron geometry, geo, I'm going to shorten it for geometry, is going to be trigonal by pyramidal. And also, since there is no lone pairs, there is no repulsion going on around the arsenic. Let me show you. There's no repulsion because, like I said, there's no electrons. It has lone pairs. We know that the molecular geometry, or molecular geo, is the same as trigonal by pyramidal. Okay, and now that we have all this information, we can actually go ahead and get into the actual 3D structure of this. So let me move some of this stuff out of the way. I'll go ahead and go over it again. But, so, the 3D structure is going to look something like this. So you still have your arsenic. That one's still going to be in the middle. You're going to go ahead and draw 2 bonds like this and 1 bond like this. Go ahead and put your F's. And since we are doing a 3D structure, what we include instead of lines for these next ones is we call it a wedge. Doesn't look the best, but it is a wedge. And this goes to show that this fluorine is actually coming towards us in the 3D. And then we show another one just like that, showing that the fluorine is going into the screen, so in that 3D depth sense. Next part we need to get into is the bond angles between these. And for this specific structure, there actually is 2 different types of bond angles for this. We have one which is the equatorial, and it is on this plane right here. So this is going to be your equatorial. Let's move this up just a tad, still right there. So that's your equatorial, and in there, in between these angles, we actually have equatorial. Its bond angle is actually equal to 120 degrees. Like I said, though, there is 2 different bond angles on here. The other bond angle is actually in the position called the axial position. So this is your axial, Think of it just like an XY axis in a sense. And then we're going to focus on this bond angle right here. That angle for the axial angle is actually equal to 90 degrees, so it does form a right angle with there. And then those are your two bond angles. So again, let's take a look at the structure. So you have your axial, your equatorial, you have your wedge of your fluorine coming towards you, the wedge or the dashed line showing the fluorine going away. Again, molecular geometry is trigonal bipyramidal. And then let's go ahead and compare these to the pictures. So as you can see, you have your 1 fluorine, 2 fluorines, 3 fluorines, 4 fluorines, 5 fluorines, and connected to them. And the trigonal bipyramidal, you have your equatorial. It's your equatorial. And again, this is your axial. The picture for, let's move this out of the way for a second. Bring in this picture right here. Same exact thing. You have your greens with the red dots. Those are actually your fluorines. And you have your arsenic in the middle. This is going to be your central atom. And then you can still see again, you have the equatorial coming this way. No, you can't really tell that well, but that is the equatorial. And then you have your axial position again right here. So in all, this is your trigonal bipyramidal. So your trigonal bipyramidal. Let me go ahead and squeeze some of this information in. That way you can see everything, you know. So first thing first, what we did, we found how many valence electrons. Then we drew the Lewis, and we found out how many bonding pairs and lone pairs that it had. From that information, we're actually able to figure out the electron geometry. Again, this is geometry right here. This is the molecular geometry. And from those, that's how we actually tell to write our 3D structure. And again, this is the 3D structure. So on here, you have your wedges, again showing the fluorines going in and out. You have your fluorine top, fluorine bottom. And then you have your equatorial, which is highlighted in the red box. That's your equatorial plane. And there's a different bond angle, which is 120 degrees, compared to the axial, which is 90 degrees. And that is everything about this.